Yeah, thank you very much for the introduction, and also from my side, a big thanks to the organizers for putting together this nice conference. And so today I want to talk about a couple of works that we did over the last couple of years. So this is together with Philip and Julian, who are both PhD students in the group of Michael Knapp at Technical University of Munich, where I was previously based, as well as with Kinde, who was a student at MIT, is now a postdoc in the group of Ehud at Berkeley, as well as with John, who's now faculty in Illinois. So I want to sort of continue the many-body CMP aspect of this conversation about dipole conserving systems, and sort of in the spirit of this workshop, because we can regard symmetry as an organizing principle which builds a bridge essentially from like a system with some microscopic degrees of freedom and an effective description which is valid for essentially the long wavelength, the low energy degrees of freedom. And so this kind of framework is of course immensely successful on the one hand for determining the low energy phases of quantum matter. For example, here is the phase diagram of a system of bosons which can opt on a lattice and which interact via local contact interactions. And then these bosons can either be in a superfluid state or an insulating Mott state. And of course, the precise details of this phase diagram will depend on the microscopics of the model, but the long wavelength description of these phases, as well as the universality classes of the transitions between them, these can be captured in some effective action, which this can be written down in terms of an order parameter field, and the form of this effective action is only constrained by the symmetry properties of the system that we look at. This same sort of thinking is also very successful in out-of-equilibrium situations. So for example, if we think about hydrodynamics, so we have some conserved charge and some initial localized charge pump in the system, and we're wondering how quickly does this out-of-equilibrium charge distribution go towards equilibrium. Then generally we can write down some effective hydrodynamics equations, like the diffusion equation, which refers only to a coarse-grained local charge density, which will determine this process. And so, of course, now we can ask similar questions about systems where we have this sort of multipole, or in this case, dipole conservation law. So, repeating what has been said, where we not only conserve a global unit charge, but now we will also conserve the global dipole moment, or center of mass of this unit. And then, again, kind of these, like integrating such symmetries into a setup leads to interesting consequences. On the low energy side of things, has been realized in this fractal elasticity duality that there's essentially duality between these fractonic constraints and elasticity theory. And from this sort of mapping, one can also infer the low energy phases that one should get in such a system, in particular something like a two-step process, where initially one is an insulating phase, but then the dipole can condensate in the first step, and in the second step also the fractons can condensate. Similarly, in out-of-equilibrium situation, the presence of this sort of dipole constraint also has led to new and interesting insights. On the one hand, depending on the microscopics of the system, the presence of this conservation law can actually break epicity, such that if you have some initial out-of-equilibrium charge distribution, it will actually not go towards equilibrium at all. Or if it does, then this process is going to proceed in an enormously slow manner. So instead of normal diffusion, you will have some sub-diffusive properties, which is a consequence of this dipole conservation law. And some of these aspects in quantum many-body systems can actually concretely be tested in the lab, as John was already alluding to before. So in particular, these non-equilibrium aspects have been verified in these systems of cold atoms. On the one hand, there's been experiments which see this type of episodicity breaking, where there's some quantity and an imbalance, which if the system would thermalize would decay to zero, but in this case gets stuck at a finite value. At the same time, there were experiments where you prepare an initial density wave mode of atoms along one direction. Along the same direction, the dipole moment is conserved. And then you simply watch essentially this density wave order decay as a function of time. And from that, you can infer the transport of the system. And it was found that this is indeed the sub-diffusive transport that comes from the dipole moment conservation. So this is nice. And on the other hand, kind of on the low energy phases of matter side, so quantum systems, which feature these sorts of constraints, the picture is a little bit more sparse because in these sort of cold atom experiments, exploring low energy properties is more challenging. So one goal that we set ourselves, and what I want to talk about in this talk today, is can we actually go sort of through this full progression of starting with a microscopic Hamiltonian, which has these types of symmetries, and then seeing how the low energy properties that we would expect from this dipole moment conservation arise, and can we also give a pathway towards seeing it in a concrete cold atomic experiment. So that's essentially the goal. And here's the concrete model that I want to talk about. So this is a Bose-Hubbard model in 1D, which conserves the dipole moment. So essentially, we have a one-dimensional chain, and the basic processes that we can have are these sort of pair hopping processes, where if you move one particle to the left, you also have to move another particle to the right in order to conserve the center of mass or dipole moment of the system. So in addition to this correlated pair hops, we will have density interactions, contact interaction between bosons sitting on the same side, as well as a chemical potential. And then this model has been studied sort of in a mean field picture in this paper here. And indeed, what I found was similar to what we saw before in this fractal elasticity framework, that there can be a phase where the system is in a mod insulating state, where both charges and dipole degrees of freedom are gapped out. But then eventually, sort of, if we increase this correlated hopping term, the dipoles can condense, and we go into a dipole condensate, where now only the charges are gapped, but the dipoles are gapless, and then eventually also the charges can be together. So we now want to see how is the situation like in one dimension. Of course, in one dimension, fluctuations, quantum fluctuations are usually large, and condensates turn into quasi-condensates. So one question is, in this 1D realization, will we get a Luttinger liquid of these dipoles? And can we actually sort of have a more microscopic understanding of this? So can we actually formulate theory in terms of microscopic dipoles moving at low energies? And can we see this sort of spontaneous breaking of the dipole symmetry in one dimension, which, even though it's a continuous symmetry, is allowed due to a modification of the Mermin-Wagner theorem for these multipole systems. And in order to do this, we sort of really utilize the 1D nature of the model that we're studying here. On the one hand, studying post-analyzation descriptions of the problem, as well as using sort of extensive matrix product state numerics in order to check that these low energy features actually emerge. So let me start by talking briefly about how we can actually kind of get out microscopic dipoles at low energies in this model. So for this, let's look again at the conserved quantities that we have. So we have a globally conserved charge, which we can simply write as the number of bosons sitting on a given site, and we look at the deviation from the average filling that we have in the system, and so this integral is going to be 0. And then we can also write the dipole moment in a particular way, and ideally we would like to see this dipole moment being written as an integral or a sum over a local bounded charge, right? So we want to have it as a locally bounded dipole density. Now, this form is not quite suitable because, as you see here, we have this factor x multiplying the local charge density. So this is not going to be bounded. But instead, we can kind of rewrite this integral as a double integral. Geometrically, it just corresponds to two different ways of computing a particular volume. And then now we get a double integral, and now sort of we have a nice way of identifying a local dipole charge. In particular, by identifying this charge as the cumulative integral over the local charge density, or in differential form, the derivative of the dipole density gives rise to the charge density. So this is now nice, because now we see if we have a system where, for example, there's a charge gap, charges are gapped out, that means charge fluctuations will be small. In particular, this cumulative integral over the charge density is always going to be of order 1. So remember, this charge density is the sort of the deviation of the local charge from its average. And if charges are gapped, then these fluctuations are going to be small. And this quantity, this local dipole density, as we've defined it here, is going to be always of order 1. So one way to express this is to say that we get this type of bounded dipole density if the structure factor of our system actually goes to 0 for small momenta as k squared, which is sometimes called hyperuniformity. So here, we have identified a condition for when we can have this bounded local dipole density. And we generally expect this to be the case when this interaction, this contact interaction between charge is very large, such that charge will be gapped out and charge fluctuations will be small. And so in this scenario, we can be sure, or we're very confident that we will have this charge gap, and then we can write down sort of an effective field theory description by simply bosonizing these like local dipole degrees of freedom that we've just introduced in a standard way, by introducing both a phase field for these dipoles as well as a density field. And then the effective model that we get out is kind of a standard Sutton-Gordon model with density interactions, a kinetic term of those dipoles, as well as a cosine term, which comes from the fact that we are on a lattice here. And then the standard scenario that we would expect is that there might be a BKT transition where, as sort of the effective Luttinger parameter of this dipolar theory increases, we go from a gapped mod state where the dipoles are gapped through a BKT transition into a phase where this cosine is now irrelevant and the dipoles become gapless and enter a Luttinger liquid phase in which we should have power law correlations. So this is kind of a simple way to get to an expectation for what we should find in this system. And now we want to check numerically that this actually happens in this microscopic boson model. So the way we do it is we use a numerical method, which is called matrix product states. So I will just talk about it very briefly here. So the general theme is that, of course, in principle, simulating these quantum systems is not so easy because the wave function that we write down for a given quantum state psi contains exponentially many coefficients, which in principle one would need to keep track of. And so matrix product states kind of give us a variational subspace of all these possible states by writing these coefficients as a contraction of a bunch of different matrices A here, which have some bounded order given by a parameter chi, which is called the bond dimension. So what we do here is with these exponentially many coefficients, but now we have essentially variational wave functions, which are parameterized only by algebraic numbers. So this we can handle efficiently. And in particular, this is kind of a clever subset of states within the full Hilbert space because it contains all the gapped ground states of one-dimensional systems. The reason for this is that the entanglement entropy that can be captured in such states goes as the logarithm of this bond dimension, and gapped ground states in one dimension have sort of a finite entanglement entropy, and therefore this is a good and accurate description for such states and such systems. And in particular, what we can rely on is that for these types of states, there's very efficient algorithms for either finding ground states or doing time evolution. So this is kind of a numerical method of choice, which is particularly well suited for this one-dimensional system that we're working in. And kind of we can indeed check that the expectation that we've had before is true. So we go, we set like an average charge density or an average filling of those bosons equal to 2 and go to a dipole moment equal 0 sector. And we evaluate the correlations of such an effective dipole creation operator. So where we create a boson on one side and annihilate a boson on the side next to it. And then in the mod state, we would expect that since dipoles are gapped, these correlations, they decay exponentially, while in the Luttinger liquid, they should decay as a power law algebraically. And indeed, we find as we sort of scan the values of this dipole correlated hopping over the density interactions U, there is at small values of this fraction, we get a mod state where kind of this axis is linear, this is log, so we get a nice exponential decay. And sort of beyond some critical value of this correlated hopping strength, now we're on a double log plot, and we see nicely how we now get the straight lines here. So that's an algebraic decay. So indeed, these dipole correlations become algebraic. And you can also see in the numerical method, what you do is you scale up this bond dimension, and then kind of as you scale the bond dimension, eventually these correlations converge to something that goes algebraic. So actually, one additional thing that we can do here with this method, which is quite nice, is we can simply take snapshots of the quantum state that we have, snapshots in the occupation number basis of these bosons according to the probability distribution that is defined by this overlay. So we can sort of very nice and visually identify what's going on here. So in the mod state, you indeed see that on top of kind of the average charge filling, you get these sort of quantum fluctuations where you have sort of these virtual excitations of a positive and a negative dipole, which are effectively bound together. But once you go through the phase transition and you enter this dipole Luttinger liquid, you now see that you have sort of these individual dipoles unbound moving through the system. It's kind of a nice visual representation which you can get from the snapshots. We can also verify more explicitly that this picture that we've had before of kind of a gapped out charge degree of freedom and a dipole gap which closes as a function of this correlated hopping, that this is actually the case. So we can simply compute the ground state energy at a given system size with a sort of certain number of particles and a certain dipole moment in the system. And then we can, on the one hand, compute something like the charge gap by simply comparing these ground state energies for a different number of particles in the system, as well as the dipole gap by doing the same thing, but simply sort of varying the dipole moment in the system by 1 unit. And then we see, again, sort of, if we do this in the mod state, and we scale up the system size, both of these gaps converge to a finite value. So both charges and dipoles are gapped out. While if we do this in the Luttinger liquid phase, then the charge gap, which is here in black, that one stays finite, while we see sort of clearly the dipole gap goes down as 1 over the system size, as one would expect in such a Luttinger liquid. And indeed, if we plot kind of this gap as a function of this hopping T over U, then we see nicely that there is a transition here where the dipole gap in red closes, where the charge gap remains open. And this is this BKT transition, which leads to this gapless dipole degrees of freedom. So here one could ask, you know, like, can we also get another transition where the charge becomes gapless as well? So actually, in this case, what we find is that charge always remains gapped out, even though the gap does become very small. But this was a simulation where we essentially fixed the particle number or the density to a given number. What we can also do is we can do a sort of grand canonical calculation where instead we fix the chemical potential, but the charge is allowed to vary. And what we then find is an interesting situation where, as we vary this dipole hopping, we are first in this mod state, as we used to. Then eventually the dipoles become gapless. We go into this Luttinger liquid phase. But what can now happen is a sort of first order jump, where now the density makes a jump, is no longer integer, and appears to vary continuously with sort of the strength of this hopping here. At the same time, we find once we are sort of in this phase here, where the filling is now no longer integer, the off-diagonal dipole correlations that before we saw were decaying algebraically, now they actually become long-range ordered. And these are, as we scale up the bond dimension to pretty high values, we see that kind of more and more we see like this true off-diagonal long-range order in these dipole correlations. So it seems like we're finding a state where we actually have spontaneously broken the dipole U1 in this one-dimensional system. So it turns out that this is actually a little bit surprising. So we would expect that if we are at some kind of rational filling, that kind of the effective model for such a state where now both dipoles and charges are gapless is effectively given by such a Lifshitz model, where now we're writing down things in terms of the charge degrees of freedom, and we have a normal density interaction between the charges. The usual kinetic term cannot appear because it violates the conservation of the dipole moment. But the next term that can appear and that is consistent with the dipole moment is this sort of term where we have two derivatives of this phase field theta. So that model, in principle, if we only take those first two contributions, is consistent with all the numerical results that we find here. But of course, because we are on a lattice, there should also be this cosine term. And it turns out that for this Lifshitz theory, actually this cosine term is always relevant. And so in principle, we always actually expect the charge to be gapped out in this one-dimensional system due to lattice effects. But kind of in practice, what we're finding is that this charge gap can apparently be tiny, which might depend also on the microscopics of the system. But if that's the case, then we essentially find kind of physics which is consistent with this Lifshitz theory, even on 3D long length scales in the numerics that we can do here. So this is also apparent when we look at dynamical quantities, which we can compute in our MPS framework. In particular, we can compute the spectral function of the dipoles. And then we see, okay, here kind of in the mod state, everything is as we would expect. We get a nice sort of gapped out cosine band. In the Luttinger liquid, we already see that although kind of this dispersion goes sort of towards zero momentum in a linear way, we already see that kind of there is this quadratic part reminiscent of this Lifshitz theory that is clearly observable already here. So essentially the yellow dotted line that we can put on top of the numerical data, that's kind of the dispersion that you would get by adding a small gap to the Lifshitz model, which has a quadratic dispersion. But at the very lowest momenta, this actually does become linear and agrees with the velocity that we can extract from ground state correlations in this Luttinger liquid phase. And then if we go to sort of non-integer filling, for example, filling 5 fast states, indeed now sort of the spectrum that we find here looks like it's completely dominated by this Lifshitz theory. So here we get a sort of a nice quadratic dispersion, which actually becomes soft again at pi. So in addition to this off-diagonal long-range order and this quadratic dispersion, the system actually sort of breaks translation invariance and forms a charge density wave state. So in some sense, we have the coexistence of this off-diagonal dipole order and a density wave state. So it's in some sense, quotation marks, like a supersolid to some extent. So these types of dynamical signatures would be something that would be nice sort of to explore in an experiment. But of course, these spectral functions are actually kind of hard to access in cold atomic setups. So it would be nice if we could come up with a different way of sort of preparing these sorts of states and then verifying that we actually have them. So we look at a different type of experiment that one could imagine, and that's the following. So let's say we have sort of our dipole conserving system, and we're in one of those ground states that we've just introduced. So one experiment that we could now make is, let's say, on top of this ground state, we create like 2 charges, 2 fractons, essentially, that sit at some given distance from each other. Now, what can happen is that we can move a charge, but because dipole moment is conserved, we need to create a dipole. And then this dipole can essentially move and then be absorbed by the other charge sitting here. So it's like there is an effective hopping process, like a long-range correlated hopping process between those charges, but it has to be mediated by this effective force carrier, this dipole. And then, of course, this process will be susceptible to whether the dipole that we have to kind of send from one fracton to the other is either gapped or gapless. If the dipoles are gapped out, then the further these 2 charges are apart from each other, the smaller this effective correlated hopping process should become. And effectively, like the 2 fractals should be sort of confined to each other and only undergo some sort of small scale oscillations. And this is indeed what we see. So if we are in this mod insulating phase where the dipoles are gapped and we start with such an initial state, then we see where kind of the 2 fractals sit directly next to each other, then we see they only go a little bit of back and forward oscillation, but otherwise they're essentially remain in place. And once we sort of go across the transition and we go to a value of this dipole hopping, which brings us into the Luttinger liquid phase, now we see that actually more things happen, stuff happens. So in particular, we find that there is sort of this central blob of charge, which now actually starts to broaden. And if we look at it in a little bit more detail, that's sort of the red curves here. This is the density at the original point where the fractons were sitting. Then numerically, we find it approximately sort of goes down as 1 over square root of time. So there's some sort of diffusive process which scales diffusively, with which these 2 fractons are moving apart from each other by sending sort of these gapless dipoles from one fracton to the other. But now, of course, we're also seeing that, apart from this sort of central blob, there is even more stuff. There seems to be some sort of ballistic front from which we get these oscillations, which then, however, also kind of bend around. So you can ask what this is. So if we take a line cut here, essentially, or we take a line cut, but at different times, and kind of we plot the charge distribution that's shown here in a rescaled way, where sort of along both the sort of the bond index, which just means sort of the site index of the system, we rescale this with square root of time. and we also square sort of this charge density that we locally find as a square root of time, then we get a scaling collapse. So what this means is actually that we can see sort of the Lifshitz physics that comes in at higher energies in the system. So if we took a Lifshitz model and computed what we would expect for such a process, we would find essentially like a cosine of this position squared over time, right? So, and this is exactly what we see in this numerical data here, that approximately, so behind this sort of linearly moving front, there is approximately this cosine of J squared behavior, which we see here in the numerical data of this crash experiment. So kind of to summarize this part, we see that indeed, if we do an experiment like this, there's a dynamical way of telling apart this mod insulating phase and this gapless dipole Luttinger liquid phase. And kind of from the structure, you can even see that, there is this sort of Z equals 2 physics going on above the ground state. So, of course, the question is, could we actually see this potentially in an experiment? John was alluding to this before. So how would we actually realize such a system? Well, we can start with a normal Hubbard model, which has normal kinetic hopping terms, but we add a strong linear tilt. And then there's sort of alternatively, we create these correlated hops by realizing that in order to sort of conserve energy in this model, we cannot simply hop a particle up or down this tilt, but we need to move one up the tilt and one down the tilt in a correlated way. And then doing this, there's sort of an effective Hamiltonian that describes the system that actually comes out right and contains these correlated hopping processes. And so now the procedure is very simple. So you would prepare an initial state where you have a certain number of particles on each side of the system. Then you switch on the strong tilt, and you slowly ramp up sort of the kinetic part of this Hamiltonian, which hopefully adiabatically sort of starts in this mod insulating state, but goes towards this transition into this gapless dipole Luttinger liquid. And once you kind of you stopped somewhere, then you kind of add 2 particles to the system. You could either add 2 particles or kick 2 particles out. This is approximately gives the same results. And then do the time evolution and see whether what we found previously also emerges here. And then indeed we see kind of, let's say, promising signatures that when this tilt or like this hopping, the T is small, the ratio of tilt over hopping is large correspondingly. So this is where we should still be in this mod insulating phase. Then indeed, if we look at the charge profile at different times, then these 2 particles, they just remain next to each other essentially and do a little bit of forward-backward oscillation, but generally don't move. While if we go to larger values of this hopping T, which gives us larger values of this these correlated dipole hops, then we see something that is more consistent with the second option, where if we now plot the charge density at different times and rescale it in this diffusive way, where sort of the spatial index is now rescaled as a square root of time, we get a scaling collapse, which indeed indicates that we get this sort of diffusive broadening of the charge distribution. And we can even see sort of some of these oscillations, that are sort of reminiscent of this very strong oscillations, which are indicative of this kind of k-squared dispersion, which comes in at higher energies. So we see that indeed, kind of there's interesting features in this one-dimensional dipole conserving system, which we can access. So there's this transition, gap state, and this dipole Luttinger liquid, which has some interesting signatures in the quench dynamics of the model, and which we think is actually realistic to be observed in these cold atom optical lattice experiments. And so with time that I still have, let me sort of now make a bit of a switch and kind of step away from these ground state properties that we looked at, but sort of one feature I want to keep, and that's sort of this boundedness of charge fluctuations in the system. So we saw before that we get sort of a nice picture of a bounded dipole density if the charge fluctuations are small, and more quantitatively if the structure factor in the system, so the charge correlations go to 0. as the momentum goes to zero. So we saw that we get this in sort of this ground states, when you have like short range repulsive interactions between our particles. But there could be other scenarios where we get this sort of property. So for example, depending on the specific microscopics of our system, there might be, we might live sort of in a sector where this property is just always true. Or we could have systems where there's like a long range repulsive interactions between charges, and therefore even at finite temperatures, this property will remain true. And so one question we could ask is, let's say this property is given, and you're in an out of equilibrium situation, then how quickly would your state typically relax towards equilibrium if this property is true? And so this is something we looked at among other things. In this work here, where essentially we looked at Brownian Hamiltonian dynamics. So we take some density matrix as an initial state, and then you time evolve it essentially with a random Hamiltonian, which, however, is supposed to conserve certain symmetries of the problem, like its charge and dipole moment conservation. And then what one can do is one can map this process upon averaging over these random Hamiltonians to a setup where we evaluate or evolve the density matrix as sort of a quantum state in a double Hilbert space via some imaginary time evolution towards its ground state. Now, in a given sort of sector, or Krylov sector of the model that we live in, the ground state can be written down exactly, and it's so essentially the sum of all states which live in this sector. And that's sort of the ground state that this imaginary time evolution will get us to. And then if we want to determine how quickly we will reach this ground state, we have to make a statement about the excited states of this sort of effective Hamiltonian or the Bladian that's written up here. And we can make an ansatz, a single mode approximation for these excited states by simply taking this ground state and applying like a density modulation on top of it. So we apply this charge operator at some momentum k to this ground state, and this has to be normalized via exactly this structure factor here. Then if we do this, we can essentially compute the energy of this variational state for the excited modes. And this energy essentially gives us the decay rate towards equilibrium. And this comes out exactly as k to the power 4 divided by this structure factor. And this is kind of interesting because what this means is that in a more generic scenario where sort of charge fluctuations are not bounded, so the structure factor is just order 1 as we go to low momenta, this gives rise to a subdiffusive process where essentially the relaxation rate scales with the momentum to the 4th power. This is sort of this fractal hydrodynamics that conventionally holds. But if we are sort of, for some reason, in a sector where we have this bounded fluctuations, then actually we get out sort of normal diffusion again. And we also check this numerically, so we can run some sort of simple 1D circuits where we have charge conservation, dipole conservation, and we find sort of a Krylov sector where this sort of bounded charge fluctuations are always there, and then we can compare this to the case where we're in a more generic setup, and indeed also here numerically we find that in this case we get sort of this diffusive relaxation of the charge density, while if we're in a more generic setup we get this dipolar subdiffusion with t to the minus 1/4. And so here kind of this bounded charge fluctuations were directly incorporated into the connections of the state space that we're working in. But there's other scenarios where we could think about actually getting these properties. So for example, if you had some charge density, which is given via some Gauss law, where the divergence of some electric field, then sort of quite naturally, if you look at the charge that's inside some volume, it's going to be given as the boundary integral over the electric field. But generally, right, the electric field will be sort of cut off, right? Either because there's some sort of square term interaction, or if we work with a quantum link model, then the values of the electric field are naturally cut off. So this is sort of in some sense an effective way to include Coulomb interaction, and therefore have a long-range repulsion, which enforces kind of the area law properties of the charge fluctuations in the system. And in such a case, if such a system has dipole conservation, then we would actually expect that the relaxation rate is not this k to the 4 subdiffusive process, but becomes diffusive as a consequence of these boundary charge fluctuations. Good. So with that, let me conclude and give a brief summary. So we investigated these concrete dipole conserving lattice models. We found there's an interesting phase diagram where you can essentially get this multi-step process of having a fully gapped system, then the dipoles condense, and then eventually even the charges can become gapless here in these numerical results. We've investigated dynamical signatures of these phases and how we can potentially see this in concrete lattice model experiments. And kind of inspired by this, we took a property that we've used, which was this boundedness of charge fluctuations, and we've determined how out of equilibrium systems in the presence of these fluctuations behave. With that, let me thank you for your attention.
Here you define this dipole operator as following: d dash I is equal to bi dash bi plus 1 dash bi. Right? So can we define the dipole operator as following: bi dash I plus 2 bi? Basically, I was wondering, do the physical results depend on this definition of the dipole operator?
Right, good, yeah. So, right, so if here we didn't have a +1, but a +2, then we would qualitatively get the same results, that the correlations would be exponential here and algebraically over there. Of course, we cannot let this distance become very large. And actually, I'm not entirely sure, like if I looked at these correlations and I would, systematically increase this distance, then as a function of this distance, what would happen? Eventually, you would have to go over, if you're in this lattice liquid phase. If this is just, +1, then okay, we see this algebraic decay. If it's, some very large distance, it probably have to become exponential again. I'm actually not entirely sure, how this crossover would proceed. So there's a good question.
So in some continuum models that are like a breakfast model but larger and so on, they see also like you can have a phase where let's say the dipole symmetry is spontaneously broken, and another phase where the monopole and the dipole symmetry are both broken. In the dipole phase, the order parameter is a 2-point function, and in the other one is like a 1-point function. So is there a similar picture in the phases you see? If you try to go to the continuum.
Say again, so here, like the order parameter here, we look at essentially this dipole correlation function, right? And your point was, in the continuum models, there is a field which is charged under the monopole and the dipole. And if the 1-point function is non-zero, then you have both symmetries are spontaneously broken. Oh, I see.
But if the 1-point function is 0, but the 2-point function is non-zero, then you have only the light.
Oh, okay, good. Yes. Right. So I guess that would just be sort of testing, just these operators B. Right? If you take the expectation value of B, you find a non-zero value, then you must be in then the charges must be condensed also. Right? While if sort of B dagger B has a finite value, but B in and of itself does not, then only the dipoles have condensed. And kind of this is what would happen here. So, okay, maybe like one point to note here is that in the numerics that is shown here, we explicitly enforce the dipole symmetry. So it cannot spontaneously break in the numerics that we do. So what we have to look at are sort of the correlation functions of this dipole operator D. If the system were allowed to actually spontaneously break, then this operator D would actually acquire a finite expectation value, but the single B operator would not, which is exactly this scenario that 2-point correlation has a finite value, single point correlation does not, which I think would correspond to what you're saying. Thanks.
Thank you for very interesting talk. So yeah, you mentioned this phase transition from dipole mode to dipole Luttinger, then to some superfluid. And I was a bit confused because at some point you mentioned that Lifshitz kind of effective theory is non-relativistic dx squared phi squared. Does that describe the dipole superfluid or superfluid phase? Yeah,
Yes.
which region does this describe?
Sorry, what's the reason?
Yeah, which area, which phase?
Oh, okay, good. Yeah, right. This is sort of in this phase here,
okay.
where so you can show that if you took like this clean Lifshitz model, you would indeed get a compressible state, which is what we see here because the density varies smoothly.
Yeah, but then you mentioned that you always expect the charge gap. But then the dipole superfluid phase, if I understand correctly, there should be no charge gap. Or...
Right, exactly. So that is sort of a numerical finding here. That in principle we always expect the charge to be gapped out. In practice, we find that apparently this gap can be so small that on the system sizes that we can access numerically, you don't see it. And therefore, it like in the numerics, it looks, just like you would expect sort of from the clean Lifshitz.
So if you can calculate everything exactly, then this charge density as a function of hopping should look like a very tiny step.
That would be the expectation, exactly.
Thank you.
There's like one last question before we go for coffee. Thanks. Can you go back to the slide where you showed the projection from the original Bose-Hubbard Hamiltonian with field onto the...
This one?
Yes, this one. So first question, or actually, sorry, two short questions. First question, did you try, is there any evidence, numerical evidence, that the physics you described within the projected dipole Hamiltonian can be observed also at least partially when just running the tilted Bose-Hubbard model itself?
Right, sort of that's essentially the kind of the data that is presented here. So here like the full process of preparing the state and then looking at the dynamics, but that is really run in this full Bose-Hubbard model with this tilt and not this effective model that you will get out perturbatively. And then sort of our statement is that approximately we see qualitatively the right behavior, that here sort of if we have two charges, they're essentially stuck, while on this side, when the dipoles are gapless, then they can spread.
I see. And the second question is, if I look at the effective Hamiltonian, it seems like the Hubbard interaction can be scaled out more or less completely, because TD is proportional to U and U is proportional to U. So what does that mean? Does it mean that I can tune U now down to 0 because the physics is still the same?
Well, in principle, to first order, that's true. In practice, of course, one needs to be careful because there's in an actual experiment, we don't have an infinite time budget. So like the actual value of this U will be relevant for practical purposes. But it is true what you're saying, that in this perturbative way, U always appears as a prefactor in front of this correlated hopping and the density interactions.
All right, if there are further questions, we can do this over coffee maybe, and let's thank the speaker again.